Recursion is the process in which a function solves a problem by calling itself. Problems that work well with recursion are those that can be split into subproblems. For example, computing the factorial. 4 factorial is 4 times 3 times 2 times 1, which is 4 times 3 factorial. What is 3 factorial? Well, it's 3 times 2 factorial. What is 2 factorial? Well, it's 2 times 1 factorial. You can see here how the main overarching problem of 4 factorial contains within it smaller subproblems of the same nature. To work out the main problem, you would need to work out 3 factorial, and to work that out, you would need to know 2 factorial. We keep moving further down the tree, with each function having a dependency of some kind, until we reach the base case. The base case in this scenario being that 0 factorial is just 1. As a result, there are no more unknowns in the computation of 1 factorial. We know now that it's just 1. Likewise, if we know 1 factorial, there is now no unknowns to compute 2 factorial. So we know the answer to 3 factorial, which is 6, and then we know the answer to 4 factorial, which is 24. Due to Haskell being a purely functional programming language, the fundamental way in which we perform iteration is through recursion, where a function calls itself. Understanding recursion is important because it helps you think in a functional way, especially if you're coming from an imperative background. Recursion is the basis for higher order functions such as map and fold, so understanding how these functions work under the hood can give you a better understanding of the language and how it is designed. Let's look at the same example that we saw on the slides, calculating the factorial. This is how we would do it in Haskell. We can define a function called factorial that takes an integer as input and returns an integer. Recursion, as we mentioned before, occurs when a function calls itself. The function would need to call itself over and over again infinitely if we don't define some base case, the smallest subproblem that we can solve. In this case, it is that the factorial of 0 is 1. We can't go any deeper than that because the factorial of a negative number is undefined. Then we can define how the function calls itself. We're saying here that the function receives an input of some number n. The factorial of n is then multiplied by the factorial of n minus 1. For example, the factorial of 4 is 4 multiplied by the factorial of 3. If we run the code with 4, we can see that we get 24 as expected. Once the process of recursion is understood, the next challenge is learning how to solve problems in a recursive way. Recognizing common patterns that recursive problems share can be an effective way to tackle this. You have some problem that you want to solve. If during the process of solving it, it is apparent that the problem relies on subproblems of a similar nature, then recursion might be a good way to solve it. There will be a base case as part of each recursive solution. Think about what input would be the smallest that you could provide. What subproblem wouldn't rely on any other subproblem? Then lastly, closely connected to both these points, how can you continue to reduce the input size? What will be the operation that you perform to make sure that the recursion continues to progress deeper? Let's take a look at some more examples and walk through the thinking behind them. Hopefully you'll start to see some similarities in each recursive solution. We can also perform recursion on lists in Haskell. So we could do it using an implementation like this. So note before I begin that Haskell has a built-in function called reverse. So this is why we've got the quote mark here, just to differentiate between the function that I've created here and Haskell's built-in function, also called reverse. So how do we break this problem down? Well, to reverse a list, the first thing we need to do is move the first element to the end. So we can do this by splitting the list into a head and a tail, and this pattern here allows us to do it. So x would just be the first element in the list, the head, and xs would be the rest of the elements in the list, which would be known as the tail. So we take the head of the list and we place it at the end of the reversed tail. Now, how do we reverse the tail? Well, the way we do it is we pass it back into the reverse function that we've created, because it in itself is just a list as well. So this is where the recursion is happening, because we're calling the function within itself. So we keep doing that, and because we're splitting the list each time, it's going to get smaller and smaller, and eventually we're going to arrive at a case where we just have a list with one element. Now, the reverse of a list with one element is just the element itself. So that's going to be the head when we split the list again, because lists are linked lists in Haskell. So when we split it, we're going to be getting the head, which is just going to be the element itself. And then the rest of the list is just going to be an empty list. Now, because it's an empty list, we can't go any further. So this is going to be our base case. So we're saying here, when we do hit this base case, that the reverse of an empty list is just an empty list. So now we've reached the base case, the recursion can begin to unwind because we can start to properly reverse all of the subproblems, and then that leads us eventually to the full list being reversed. So we can see this in action by running the code. Here we're providing an input of a list which just contains the numbers 1, 2, 3, 4, 5, and then we're calling our recursive reverse function with the input list here, and then we can see that we get the reversed version of the list as the result as expected. Calculating the Fibonacci sequence is a common example of a problem that can be solved recursively. It's the series of numbers where each number is the sum of the two preceding numbers. The function here will take as input some integer, n, and return the integer in that place in the sequence. For example, fib6 would return the sixth number in the sequence. Note this implementation is zero indexed, so we assume the first number in the sequence to be 0. Let's take, for example, the sixth element in the sequence. So to calculate the sixth element, we need to find the fifth element and add that to the fourth element in the sequence, the two preceding numbers before the sixth element. We don't necessarily know the fifth number in the sequence or the fourth number in the sequence yet, so these are smaller subproblems. So the way that we find them is we call our Fibonacci function again, but on the fifth number and the fourth number. And for example, if we were calling it on the fourth number, we would need to know the third number and the second number in the sequence. And you can see how the recursion goes deeper and deeper until we eventually arrive at the last two numbers in the sequence, 0 and 1. These numbers won't have two preceding numbers before them. As a result, the recursion should end when we reach either of these two numbers, and thus we have our two base cases. So the 0th element is 0 and the first element is 1. Like before, when we reach these base cases, this will then activate the unwinding process. So we know the answers to the smaller subproblems, and we build our way back up to eventually arrive at the final answer. So the sequence of Fibonacci numbers will be calculated and we'll arrive at the answer expected for our input. So in this case, we're looking for the sixth number in the sequence. If we run the code, we can see that we get 8 back as expected. Let's have a look at another example. Here we want to count the number of occurrences of an element in a list. So say we have a list of 3 elements that we're going to pass as an input. 2 of these are the number 1. So we pass the number 1 into the function and we're looking for the number 1 within the list and how many times it occurs. So the answer for this example should be 2 because there's 2 number 1s in the list. We could do something like this recursively in Haskell. So first we define the equality type class constraint to specify that the element we're looking for and the elements in the list can be compared with the equality operator. We define the function to take 2 arguments and split the list into a head and a tail. We begin by checking the first element, the head of the list. Guards are used in this scenario because we have multiple conditions to the recursion. Either the element at the front of the list matches that we're looking for, in which case we add 1 to the count, then call the function again on the rest of the list, or the element at the front of the list doesn't match the element we're looking for, in which case we don't increment the count, but like before, continue by calling the function on the rest of the list. That smaller list will be split, same as before, into head and a tail, and the comparison will be made again over and over. Eventually, the head of the list will be just one element. It will be checked to see if it matches what we're looking for as usual, but the tail will be an empty list. At this point, we can't go any further, so we've reached the base case. We know that the number of items in an empty list that match the item we're looking for has to be 0. As a result, no more subproblems rely on each other, so the recursion unwinds as usual. Whenever there is a match, the count would have incremented. This all adds up to provide the overall count for the original list. So we can see if we run the code, we get the number 2 as expected because there's 2 number 1s in the input list. I also wanted to briefly mention before the end of the video, tail recursion. So this is a type of recursion where the recursive call is the last statement that is executed by the function. Usually this can be beneficial to implement because it removes the need to hold lots of function calls in memory. However, Haskell evaluates in a lazy manner, meaning it doesn't need to immediately build up a call stack like in strict languages. Because it doesn't need to store lots of function calls on the stack, even for recursive functions, tail recursion wouldn't be as significant as an optimization, so I'm not going to look at it in this video. But that was a look at recursion in Haskell. Thank you for watching.